Welcome back to Chapter 3 of Principles of Mathematical Analysis. In this short but important section, we introduce the idea of absolute convergence. A series converges absolutely when the series of absolute values converges. The central fact is that absolute convergence is a stronger condition. If a series converges absolutely, then it converges in the ordinary sense as well. We will prove this in a single clean step, and then step back to see why absolute convergence is the dividing line that organizes everything we have done with series so far. The convergence tests we built earlier, the comparison test, and the root and ratio tests all turn out to be tests for absolute convergence. Let's begin. Here is the plan. We start with motivation, recalling the difference between a series and the series of its absolute values, and asking why that distinction matters. Then we give the definition of absolute convergence. Next, we state and prove Theorem 345, the result that absolute convergence implies convergence. After that, we work through the remarks in 3.6, which explain how absolute convergence relates to our convergence tests, what non-absolute convergence means, and why absolutely convergent series behave so nicely. Finally, we summarize. Let's set the stage. So far, we have studied a series sum of A sub n, asking whether its partial sums settle down to a limit. But there is a second series hiding in plain sight, the series of absolute values, some of the size of A sub n. This second series throws away all the sign and cancellation information and just asks how big the terms are. The relationship between these two series is the whole subject of this section. Next, let's see why the two can behave very differently. Here's the key tension, shown on the slide. The alternating harmonic series, sum of -1 to the n over n, converges. We proved this back in the section on summation by parts using the alternating series test. Yet if we replace every term by its absolute value, we get the ordinary harmonic series, sum of 1 over n, which diverges. So this series only converges because of cancellation between positive and negative terms. Its convergence is fragile. Next, let's name the stronger, more robust kind of convergence. This leads to the central question of the section, stated in the third bullet. When does a series converge for a more robust reason? One that does not depend on delicate cancellation between terms? The answer is absolute convergence. When the series of sizes already converges, the original series is convergent in the strongest possible sense, and as we will see, it behaves almost like a finite sum. Let's make this precise with a definition. Here is the definition, shown in the blue box. We say, the series sum of A sub n converges absolutely when the series of absolute values, sum of the size of A sub n, converges. Notice this is a statement about a different series, the one built from the sizes of the terms. The terms themselves can be real numbers or complex numbers. In either case, the size is the absolute value, or for complex numbers, the modulus. Because the sizes are non-negative real numbers, we can attack the series of sizes with all the tools we developed for series of non-negative terms. Next, the main theorem. Here is the main result, Theorem 345. If a series converges absolutely, then it converges. In words, the stronger condition on the series of sizes guarantees ordinary convergence of the original series. The diagram captures the logic. the solid orange arrow on top points from absolute convergence to convergence, because that implication always holds. The faint dashed arrow curving back the other way is labeled not in general, because the reverse fails. The alternating harmonic series converges without converging absolutely. So absolute convergence is the genuinely stronger condition. Let's prove the solid arrow. Before the formal proof, here is the strategy. Our goal is to start from the assumption that the series of sizes converges and conclude that the original series converges. We will use just two tools. First, the triangle inequality, which bounds the size of a finite sum by the sum of the sizes. Second, the Cauchy criterion for series, Theorem 3.22, which lets us prove convergence without knowing the limit in advance. The idea is to transfer the Cauchy condition from the series of sizes, where we are given it, over to the original series, where we want it. Let's recall the Cauchy criterion. Let's recall the tool shown in the red box. The Cauchy criterion, Theorem 3.22, says a series converges exactly when its tail sums can be made arbitrarily small. Precisely, for every epsilon greater than 0, there is an integer capital N, so that the size of any block of terms from index n to index nm stays below epsilon, as long as both indices are at least capital N. The advantage is that this is an internal test. It never mentions the limit, only the terms. Since we are assuming the series of sizes converges, that series satisfies this same criterion. Next, we use the triangle inequality to connect the two. Here is the heart of the proof, the inequality in the green box. For any finite block of terms, the size of the sum is at most the sum of the sizes. This is just the familiar triangle inequality. The size of x plus y is at most the size of x plus the size of y, extended from two terms to a whole block by applying it over and over. Its importance is that it links the two series term by term. Whatever a block of the original series does, it is trapped underneath the same block of the series of sizes. So if we can make the blocks of the series of sizes small, the blocks of the original series are forced to be small too. Next, we combine the two facts. Now we put the pieces together. Fix any epsilon greater than 0. Because the series of sizes converges, the Cauchy criterion gives an integer capital N, beyond which every block of sizes is at most epsilon. Now chain the inequalities, as on the slide. The size of a block of the original series is at most the block of sizes, which is at most epsilon. So the original series also satisfies the Cauchy criterion with the very same capital N. By Theorem 3.22, the original series converges. That completes the proof, and the boxed statement records the result. Next, some remarks that put this theorem in context. The first remark is a simple but useful observation in the gray box. For a series whose terms are all non-negative, absolute convergence and ordinary convergence are exactly the same thing. The reason, on the slide, is immediate. If every term a sub n is non-negative, then its absolute value equals the term itself. So the series of sizes is literally the same series. This is why all the work we did on series of non-negative terms transfers directly to absolute convergence. Next, the case where the two notions truly differ. The second remark introduces a name for the fragile case. If a series converges, yet the series of its sizes diverges, we say the series converges non-absolutely. The example, shown on the slide, is our old friend the alternating harmonic series. It converges by the alternating series test, theorem 343, but the harmonic series of its absolute values diverges. So non-absolute convergence is exactly the phenomenon we flagged in the motivation, convergence that depends entirely on cancellation. Next, how this connects to our convergence tests. The third remark is a clarifying one. Look back at the convergence tests we have built, the comparison test, the root test, and the ratio test. Each of them works by bounding the sizes of the terms. So in truth, they are all tests for absolute convergence. When one of them succeeds, it proves the stronger statement that the series of sizes converges. The flip side is on the next build. They say nothing about non-absolute convergence. Continuing the third remark, because those tests detect only absolute convergence, they cannot tell us anything about a non-absolutely convergent series. For a series like the alternating harmonic series, the root and ratio tests are silent. The right tool there is summation by parts from the previous section, which gave us Dirichlet's test and the alternating series test. So the two halves of our theory fit together. Absolute value tests on one side, summation by parts on the other. Next, a note on power series. The fourth remark connects to power series. Recall from theorem 339 that a power series has a radius of convergence, capital R. The remark sharpens that picture. Inside the circle, that is, wherever the size of Z is strictly less than capital R, the convergence is actually absolute. The diagram shows the disk of radius, capital R, shaded as the region of absolute convergence, with the center at 0. This follows from the root test applied to the terms. The boundary, where the size of Z equals capital R, is a separate and often delicate question, exactly the kind that summation by parts addresses. Next, the biggest payoff of absolute convergence. The final remark is the deepest in the gray box. Absolutely convergent series behave very much like ordinary finite sums. With a finite sum, we freely reorder the terms and multiply two sums out, term by term, and nothing changes. The remarkable fact, which we will prove in the coming sections, is that absolute convergence is exactly the condition that lets us do the same with infinite series. We may rearrange the order of the terms, and we may multiply two series together, all without affecting the sum. Next, the warning for the other case. But here is the warning on the second line. For non-absolutely convergent series, all of this breaks down. Rearranging the terms can actually change the sum, and in fact, by a theorem of Riemann that we will meet as theorem 3.54, a non-absolutely convergent series of real numbers can be rearranged to converge to any value we like, or even to diverge. So absolute convergence is not a technicality. It is precisely the license that makes infinite series safe to manipulate. Let's summarize. Let's review what we covered. First, the definition. A series converges absolutely when the series of the absolute values of its terms converges. This is a condition on the sizes alone, ignoring sign and cancellation. Next, the main theorem. Second, the main result. Theorem 3.45. Absolute convergence implies ordinary convergence. The proof was short and clean. The triangle inequality bounds each block of the original series by the corresponding block of the series of sizes, and the Cauchy criterion then transfers convergence from one to the other. Next, the converse. Third, converse fails. A series can converge without converging absolutely. The alternating harmonic series is the standard example, and we call this non-absolute convergence. Our main convergence tools, the comparison, root, and ratio tests, are really tests for absolute convergence, so they say nothing about the non-absolute case. Summation by parts fills that gap. Next, why we care. Finally, the payoff. Absolute convergence is exactly the condition that lets us treat an infinite series like a finite sum. We may rearrange its terms and multiply two such series together without changing the result, while for non-absolutely convergent series, this can fail dramatically. This sets up the next section on the addition and multiplication of series, where we will see these manipulations carried out and proved. Thanks for watching, and see you in the next section.